So yesterday we talked about calorimetry here, of course. We went through all the notes here yesterday. You guys, if you missed yesterday, make sure you get those from somebody. And we got to our first problem here, if you remember. And I'll kind of go over this with you again here today, just to kind of refresh your mind here. Remember, yesterday we did also talk about the fact that, there's two ways we find energy, right? We find energy through Q equals mc delta T. And we also find it through this formula here. So let's not forget these two here, of course, and where delta RH, of course, is the molar enthalpy here, and the number of moles gives us the delta H, okay? So the first question that we used here yesterday, it was basically, if you remember the aluminum chunk, right? We're heating it up, and we're going to put it into the water, and of course the aluminum is losing the energy, the water was gaining energy. Yes, remember from yesterday? So we said, remember, don't forget here, delta E gained has to equal delta E that's lost here, okay? We decided yesterday, remember, it's always easiest to pick which one gains energy and which one's losing the energy, right? So water in this case going up in temperature, so this is gaining the energy from yesterday, and this was losing it, all right? Don't forget there's a negative there, because if you don't have the negative, things are going to get messed up, okay? The negative has to be there, of course. So we said negative mc delta T for the aluminum block, right? We said the mass of the block. Now, yesterday we changed it to kilograms, and you don't have to in this particular example, but it's not a bad idea, because the other examples you're going to see, you're probably going to want them in kilograms, all right? So just kind of keep that in mind. All right. So I think we will stick with this, and we will change this to kilograms here. So we said what? 0.05250 kilograms here. All right. And yesterday, this is where I screwed up, of course. I said, what's the specific heat capacity of aluminum? And I put that in there originally. And then I thought, well, maybe I should read the question. Yeah, probably not a bad idea. And it says actually here, calculate the specific heat capacity of aluminum. So actually, that's what we're looking for. We're looking for C here for that aluminum is what we want to find, okay, from yesterday in this particular one. The delta T, if you remember, was the final minus the initial. So remember, the aluminum is going down to this temperature here. That was your final temperature. This was your initial temperature here. So if we put in here 23.2 minus the 90 here, don't forget that was actually negative 66.8 degrees Celsius. Right? Is it 66? Double checking? Yeah? All right. So that takes care of that side there. Okay? On this side, what's gaining the energy? It was water. Remember? So we said, well, there's 148.5 milliliters of water. Remember, that's 148.5 grams of water. And since we use kilograms on that side, we better use kilograms on this side as well. We better keep it the same. So over here, we're going to put in here 1.1485 kilograms. We're going to multiply that by the specific heat capacity of water, which is 4.19 joules per gram degree Celsius. And remember, the water now starts at 18, and it ends up at same temperature, 23.2. So that was a difference of what, 5.2, I think, yesterday? So 5.2. And that kind of ran out of room there. And we would solve for C, yes? Okay. And when we solve for C here yesterday, I think we did this in class, so I think we're okay here. But basically, you're taking, I'll write it out because I'm not going to include the units here. Forgive me, 5.2 just to save a little time here. So that stuff there divided by, of course, over on this side. Don't forget there is a negative there. So 0.05250 kilograms and the negative 66.8. And of course, that would give me C. All right, good from yesterday, yeah? Yes? That gave me, as a final answer here, if you remember, was a 0.9, help me out somebody, 23 joules per gram degree Celsius. Remember, all the other units cancel. So look here, you got kilograms here. That's going to cancel with those kilograms on that side, right? I got Celsius and Celsius, those cancel. I have joules per gram degree Celsius on this side, and I'm solving for C, matches up. Okay, somebody asked, don't you want it in joules? Yesterday, I don't know if it was this class or not. And the answer is you definitely can in this case, but since the kilograms and kilograms are the two that are going to cancel, you're going to be left with joules per gram degree Celsius. It's going to work out like that, okay? The second part of this, what we didn't get done yesterday, guys, was this. It says compare it and do percent yield, percent error. So I don't do a very good job of this, I don't think, as far as Chem 20 stuff here, because I kind of do it at the end. But percent yield. To calculate percent yield, the formula is, and you might have a different one. It depends on who your teacher was, I guess. If you had me, I do this formula and then do another one after, because I think that having two of those is a little bit better than just having one formula that does everything, because sometimes it gets confusing. So I do this. I do the experimental over the theoretical. And of course, if you times it by 100, the times 100, of course, is to get it into a percentage, right? The analogy I always use is, if you get 4 out of 5 on a test, how are you going to change that to a percent? Well, you multiply it by 100, right? So experimental over theoretical times 100, okay? In our case here, our experimental value was this one right here. We just calculated this based on these experiment numbers, right? So our experiment is 0.923. What's the theoretical value? Well, this is where you're going to find theoretical value of aluminum. For a specific heat capacity, data booklet, yes? So you're going to look that up. It's 0.897, I think, yes? Is that right? So 0.897 times it by 100. And what this does is gives you what we call the percent yield. Okay, how much did you get compared to, basically how much did you get? So if you got 4 out of 5 on a quiz, you got 80%, right? 80 out of 100 is what you're supposed to get. So let's see here, 0.923 divided by 0.897 times it by 100. I get 102.8, well, 898 basically, okay, percent yield. So obviously in this case, is it possible to get over 100%? Sure it is, yeah? Happens all the time in chemistry. You get more than what you were supposed to, okay? Sources of error, things like that, whatever, right? So that can happen, right? If we want to calculate the percent error, we do this. And you may be asked for both. That's why I like to give you two different formulas for this. We take the absolute value of 100 minus the percent yield, okay? Or in this case here, the absolute value of 100 minus 102.898%, of course. The absolute value of the big bars there, you guys know what those are or no? Yes? You guys are in grade 12 now, so I assume so. Hey, you've done that probably at some point. That means you take any negatives and you basically just turn it to a positive, yes? So if I subtract 100 minus this number here, I get a negative 2.89. I'll actually just do that for this, for the first one here. So you get a negative 2.89% error, okay? Absolute value of that. I don't care if I'm over or under. All said and done, right? I get a 2.89% error, okay? And I don't care if you're above or below, you're off by some. Okay, you're off by about 2.89 here in this case. Is that good? Yeah? Okay. So there's two formulas there. And once again, you know, you can look in your data booklets. You're not going to get these formulas, right? So that's something you're going to have to memorize. You're going to have to, you know, if you want to write them down in your data booklet, fine. But just remember, you're not going to get those for quizzes or tests. So, okay? So you'll have to memorize those. If you have your own formula, like if you remember Mr. Rios' formula from last year or somebody else's and you want to use that one, that's fine. I don't care. Just make sure you get the right answer. That's all I care. Okay? Okay, good? So next example is going to be a little different. Now, we did this one solely on this last one here. Remember, what are these units here? This is kilojoules. Let's not forget. This is moles. And this is, of course, what we call molar enthalpy. So I want you to think about that term there, molar enthalpy, kilojoules per mole of something. So when the questions today, okay, the worksheet I'm going to give you is a little bit, I don't know, I would say it's not, I wouldn't say it's on the, it's not the easiest worksheet I'm going to give you, that's for sure. But remember to key in on the words. If it says something about calculate the molar enthalpy, you're looking probably for this kind of thing here, yeah? Okay, because that's the, if you look up there, that's the only thing that does molar enthalpy, delta RH, yes? So if I want to find delta RH, what else do I need to know? I need to know N, yes? True? And I probably need to know some kind of heat, right, as well. So I need to know delta H here, kilojoules. And where am I going to get this delta H from? Well, maybe from there. I don't know. We'll see, okay, as we go through some of these examples here. So let's take a look here. Any chemical reaction that takes place in an aqueous environment can have its delta H determined with a simple calorimeter. Okay, I think you guys got a few notes to write down on this part here. The examples we're going to give you here today, guys, are going to be identical to what you see, okay, for your questions today. So if you get stuck on the questions today, you need to look back at the examples and kind of see which one does this match up with, which one's kind of asking me the same thing. We're going to give you another 3 examples here. So the molar enthalpy of a solution, so the molar enthalpy, there's that term, delta solution H or delta RH or whatever, okay? Doesn't really matter. The delta RH or the delta solution H or the delta reaction H or whatever you want to call it can be measured with a simple calorimeter as well. Okay? And we'll give you a first example here of that in a sec once you guys are done copying that. Okay, good. All right. So, my next example here. Okay, I got 15.54 grams of sodium hydroxide. You're going to dissolve that into 300 milliliters of water at 20 degrees Celsius. After you put the sodium hydroxide into the water, the temperature is going to rise up to 33.8. Okay? Calculate delta solution H in kilojoules per mole. Calculate, another term that you're going to see here is calculate the molar enthalpy of the sodium hydroxide. Okay? For sodium hydroxide. So it might say calculate the molar enthalpy of the sodium hydroxide. Okay? Where are we going to start? We're going to start in the same place every time we do these questions. We're going to say, okay, well, something's gaining energy, something's losing the energy. Okay? Don't forget the negative here as well. Maybe I should have wrote that over a bit more here. Okay? First things first. Okay? Do we have any water in this container here? True? Yes? Do we have some water? What's happening to the water? Going up in temperature or going down? Is it gaining energy or losing energy? It's gaining, right? So we're going to put our water here, which by default, of course, what's giving water the energy? Well, in this case, the sodium hydroxide, yes? It's the only other thing here, sodium hydroxide. Okay? So we got 2 different parts here. Okay? Now, think about the 2 formulas we have. First of all, let's talk about water first of all. Maybe it's a little bit easier for right now. Do we have a mass of water? Yeah, we got 300 milliliters, right? Can we change that to a mass? Sure we can. Do we have C of water? Do we know C? Do we know T? Delta T? Yes, let's put that in. Mass is 300 milliliters. Now, I would definitely say change this to kilograms, okay? And if you're ever in doubt, change it to kilograms because it's going to be much easier on you, trust me. 300 milliliters is 300 grams. 300 grams is 0.3 kilograms. So we're going to put that in there, right? C, we know C, it's 4.19, right? what's delta T? Well, it's the change in the temperature, right? Water starts, it says here, it's dissolved into water at 20 degrees Celsius. It goes up to 33.8. So it looks like to me, of course, I don't know if I need to do this for you guys, but delta T would be 33.8, the final minus the initial, yes? So that's what, 13.8 degrees Celsius. Okay, so look, we got one side filled in already, yes? You know, basically what we're saying is, how much energy does it take to raise up 300 milliliters at that specific heat capacity, 13.8 degrees Celsius? Where is that energy coming from? Well, obviously it's coming from the sodium hydroxide. What information do I know about sodium hydroxide? I know the mass that I put in there. Okay? Okay, so I know M. What about C? Do you know C of sodium hydroxide? Can you look it up in the data booklet? No, you can't. Okay, it's not on there, trust me. Do you know delta T? Is there a change in the sodium hydroxide's temperature? Do we know that? No. What's the other formula you know? Well, it is, I'm going to leave the negative here, guys, N delta RH. Look at the question. It says, what's the molar enthalpy? That's delta RH, right? So I probably should use that formula instead on that side, right? Because it's the only thing that's going to give me the molar enthalpy. So it looks like to me, how am I going to figure out N? Because really, this delta RH is my molar enthalpy. That's what I'm trying to solve for, right? Calculate the molar enthalpy, calculate the delta solution H. Okay, it says SOLH there. I put delta RH, whoopity-doo, right? In kilojoules per mole for sodium hydroxide. How am I going to find N? Well, hey, how do you find N? Mass over the molar mass. What is it? 15.54 grams. Oops. 54 grams over the molar mass of sodium hydroxide. Periodic table, 1 sodium, 1 oxygen, 1 hydrogen. That's 40 grams per mole. And when I divide those two, okay, 15.54 divided by 40, oops, I get 0.3885 moles. Yes? Think of it this way. Here's another thing to think about for a second. Look up here. If this is MC delta T, this is all Q, yes? Technically? This is all the energy that's been gained, yes? Q. Q is measured in kilojoules, yes? When I divide this out, the moles, I'm going to get kilojoules per mole, am I not? Which is molar enthalpy. Yes? So all matches up. Okay? Let's move it down here a bit. So we're going to, of course, take our 0.300 here. I'm going to skip the units again just for time's sake here, guys. 13.8. And I'm going to divide that all by. Don't forget there is a negative here. Negative 3.885. Or sorry, that's not right. Negative 0.3885 moles here. Remember, if I did all the units on this top part here, it'd be kilojoules, right? Delta RH, or delta, you know, SOLH, okay? Solution H. Dividing those, times it by 4.19 times 13.8 divided by 0.38 or 3885, and I get a negative 44.7, we'll have to round it, kilojoules per mole. Okay, and does that make sense? I guess is the next question. Is the negative supposed to be there? Yeah, because when you put sodium hydroxide into water, it heats up, right? It's exothermic. So should sodium hydroxide be an exothermic molar enthalpy? A negative? Sure it should be, because it's giving off energy. The water's gaining the energy. Yes? Okay, makes sense? Questions, anyone? Yeah, no? Okay. That one's not too bad, hopefully. Okay. This one here becomes a little bit more challenging. There's a lot of stuff here. Okay. This one here says you're going to take 50 milliliters of excess copper 2 sulfate, basically CuSO4, and it's mixed with 50 milliliters. Just double check the numbers, maybe. The numbers okay, I think. Yeah, I think so. Okay. The initial temperature is 21.4, and then it's going to go up to 24.60. Calculate the delta RH, molar enthalpy, for sodium hydroxide only, once again. Okay? So, and then you're going to write out a balanced chemical equation based on this reaction here. So listen, first things first here. I guess we can start with, before we even get to the delta H delta, or which is lost and all that stuff. Look, you're going to take this solution here, and you're going to add it to this solution here, and you're going to dump them in together into here. Okay? The first one here, it says you got 50 milliliters of excess copper 2 sulfate. So let's say you got 50 milliliters here of copper 2 sulfate. Okay? You're going to mix that with some sodium hydroxide. And what is it? 50 milliliters there as well, I think. Yeah, 0.6 molar. Okay? This is Chem 20, limiting reactants. Yes? It is. Okay, when you did stoichiometry, limiting reactants. They're telling you that this is excess here. So that is not going to determine how much heat is produced from this reaction. And even if you wanted to, look, I only have 50 milliliters here. Can I find N from copper 2 sulfate? Can I find N from this beaker at all? No. Okay? There's no N there. You can't find any N. What about here? Do I have enough information? I got C and V. Can I find N from this beaker here? Sure you can. Okay? Out of these two, what they're telling you in this question is that there's excess copper 2 sulfate, which really doesn't matter in this case. And what drives this reaction is going to be your limiting reactant, which is the sodium hydroxide. Notice that's what you're solving for in this question as well. What's the molar enthalpy of the sodium hydroxide? I don't care about the copper 2 sulfate. Does it affect stuff? It does. And I'll show you how in a second here. Okay? Well, once again, E gained. Now, this is sometimes a little bit challenging for you guys to understand what's going on here. You're going to mix two solutions together. Okay? And initially, when you mix the two solutions together, or even before, they're probably sitting at room temperature. Okay? And we'd probably have to assume that they're at both the same temperature. By the way, they'd both be at this temperature there, 21.4. So this solution right here is at 21.4, and this one's at 21.4 as well. They're sitting in two different beakers. Okay? You are going to take those two beakers, and you are going to mix them together. And as you know, from Chem 20, yes? As you guys know, when you mix the two beakers together, okay, from Chem 20, you are going to get some heat that's produced, all right? Or, in some cases, some heat that's taken in. Okay, focus here. Hello. All right? What we're going to do is calculate that heat, basically, on these two reactions here. So once again, 21.4 here, 21.4. You're going to mix them together, and you're going to put obviously keep the thermometer in there, and the temperature is going to rise. Okay? So my question to you is this. When you look at this question here, what is increasing in temperature? Do we have water as part of this system here? Is there water in here? Yes or no? Is there water here? Yes, there is. Because how do you make solutions, aqueous solutions? You use water, yes? How much water do you have is the next important question. Well, first of all, before we get to that part, let me do this. If I'm looking at E gained and E lost here, is water gaining energy or losing energy then? What? Gaining. Water's going up in temperature, yes? Okay, so we're going to put water here. Water's gaining energy. All right? What's losing the energy then? Well, there's a couple things you can think of, right? Go back up to the reaction here, or go back up to this part here. Remember, first of all, look at the question. Calculate the delta RH for sodium hydroxide, right? Basically, that's telling you right there, I don't really care about the copper 2 sulfate so much. I'm kind of interested in the delta RH for sodium hydroxide. So that's probably the part you want to focus on here. That's what's going to drive this equation. Once I write out the balanced chemical equation for you, hopefully you'll see that, okay? And I'll kind of link it up for you. But this, because it's the limiting reactant, is going to determine how much heat is produced, okay? So only that. There is excess of this. Once this runs out, doesn't matter if I have stuff left over there, it's not going to react, correct? Okay? And I'll write out the equation for you after here. So we are going to put sodium hydroxide here again. Now you might say, yeah, I don't know about that. A little bit confused, and that's okay because it's your first one. But listen, it tells you that kind of right here, okay? If you're looking for delta RH, yeah, you're probably looking for the molar enthalpy, right, in the bottom part here. So once again, look, do I know, well, obviously you do because I already wrote it down, right? Do you know the mass of the water? How much water do I have? Do you know C for water? Do you know the temperature change of the water? Do you know those things? We can put those in, right? So we're going to use MC delta T on this side. What about the other side? What's the first question again? It is molar enthalpy. What's the molar enthalpy, right? So let's use this equation here again. How many moles do I have? And once again, you can put solution H there if you want. I don't care, okay? But we're going to use that on that side. And once again, we're looking for the delta RH. What's the molar enthalpy of the sodium hydroxide, yes? Okay? So listen. Here's where it gets a little tricky. I want you to look back up the question here. We took this and we mixed it with this. How much water do we have? Somebody, anyone. Throw a number out, huh? 100, yes. What needs to go in for the water? How much water are you heating up? Well, you started with 50, and you started with 50, and you mixed them together, right? So what's heating up? It's not 50 milliliters of water that's heating up, it's 100, yes? 50 from here, and 50 from here, for a total of 100. So we're going to here put 0.1 kilograms, yes? 4.19 again. And the temperature change. How much did the water increase by? Well, it looks like to me it went from, what is it here? 21.4 to 24.6. So that's what, 3.2? Yeah? 3.2. Okay? Good so far? Questions? Yes? No? All right. What's going to go on this side? Don't forget the negative. Okay. How am I going to find N? Remember, it's only based on sodium hydroxide because that's the limiting reactant. It tells you in that question, because the copper 2 sulfate's the excess. Which one's going to run out first? The sodium hydroxide. How do you find N for sodium hydroxide? Well, luckily for us, we did a little review last day, and we know that C times V will give us N. Yes? I don't care about the copper 2 sulfate. Okay? Other than the fact that I had to use it to figure out how much water I have there. But C, what's C here? 0.6 molar, I think. And what's V? Well, V is, remember, now this is where it gets tricky again. What is determining the reaction? Well, it's 0.6 with the 50 milliliters, right? That's how many moles of sodium hydroxide I have. Do I have 100 milliliters of sodium hydroxide? No, I got 50, right? This is the sodium hydroxide side, yes? This is the water side. Those two are separate from each other. I have 50 milliliters of sodium hydroxide, therefore 0.050 liters, yes? Change it to liters, of course. 0.6 times 0.05 is what? 0.03 is what I'm going to put into here. And of course, we are going to solve for the delta RH. Okay? Let me extend this a bit here. So what is delta RH here equal to? Once again, you're going to take these three numbers here. I'm not actually going to do this just for time's sake here. 0.1 times 4.19 times 3.2 divided by 0.03. Okay, and I get here a negative 44.7 kilojoules per mole. Now you might say, hey, that's the same answer as the first one. Well, it probably is. That's kind of a fluke because we're doing sodium hydroxide again. So don't freak out about that part. So that's how many joules per mole you'd get for sodium hydroxide. Okay, good so far? Yes or no? Okay, see, this isn't too bad. If you want to write a balanced chemical equation, which is the second part now, you would say copper 2 sulfate, aqueous solution, of course. This is a double replacement reaction, yes. Sodium hydroxide. You mix those two together, correct? That's what you did. Beaker, beaker, mixed them together. Like I said, sodium sulfate now, right? Double replacement, so sodium goes with sulfate. 1 plus, 2 minus, swap and drop. So Na2 sulfate, right? Aqueous, look that one up on the solubility chart. And of course, you're going to get copper and hydroxide. And we did copper 2, so you're going to get copper 2 hydroxide there, yes? So copper 2 hydroxide over here. And if you look that one up, you'll see it's a solid, I believe. It is, okay? You will need to balance it, okay? So this is same thing, Chem 20 here. Let's put a 2 here, and I think we're good, okay? Yes? Good so far. Now, that's Chem 20. Chem 30 says we need to include the heat, the thermochemical part, yes? So, where am I going to put the heat? Well, let's do delta H note. I don't know, did it say delta H notation here? Yeah, delta H notation, perfect. So we need to include at the end here, delta H, right? Yes? It's an exothermic reaction. How do I know that? Well, the temperature went up, yes? Also, look, it's negative 44.7, right? So look, here, I'm going to put negative, exothermic. Also, remember, it's 44 kilojoules per mole of sodium hydroxide. That is the molar enthalpy of sodium hydroxide, yes? How many moles of sodium hydroxide do I have in my balanced chemical equation? 2, yes? So I need to take that number and multiply it by 2. Yes, just like the formation reactions we did the other day. So what is that? 85.4? That's what I said, 89.4? You guys need to listen a little closer. Okay? 89.4 kilojoules. Remember, just kilojoules. No kilojoules per mole anymore. That's for the entire reaction, yes? Okay? Good? All right. 89.4, negative, exothermic, yes? That's how that all ties in together. Once again, okay, if we go back now and I say this, remember, this reaction is solely based on the sodium hydroxide, yes? That's it. So this, I'm telling you, determines that. We did this before, yeah? This is just review stuff, only we did a lot more calculations for it. This was the excess. So does that tell me how much heat I get? No, because I got lots of it. All right? Which one tells you? The limiting reactant tells you. Just like in Chem 20, when the limiting reactant tells you how much precipitate you get, right? The limiting reactant tells you how much heat you get. That's why we figured it out for the sodium hydroxide, because it's the limiting reactant. That's step A. Yes? Good? Questions? Yes, no, maybe so? Yeah, no? Okay. One more, right? I think one more. Whew. Yeah, one more. Are we good? It's confusing. Hey? If you get it, that's good, because this is tough stuff. Hey? The good news is that's pretty much, well, no, I'm not going to say that. All right, anyway. This one here. When you take sulfuric acid and we're going to dilute it to form 1,000 milliliters of diluted solution. The final temperature of the solution shows an increase in temperature to 3.25. Calculate the molar enthalpy of the diluted solution of the sulfuric acid. Now that sounds complicated, but once again, let's start with what we know, eh? E gain, E lost. I forgot the deltas there, but whatever, okay? What's gaining energy, what's losing energy here? Think about this. You guys did dilutions in Chem 20, yes? Right? Pipette, and you took it out and you put it in that flask and you filled it up with water, yeah? Okay? All you're doing here is diluting this solution. You're just adding some water to it. So once again, do we have water as part of this system? Sure we do. In fact, a lot of it, right? We start with 25 milliliters of this acid and we fill it up to 1,000. Okay? So do we have water? Yes. Is the temperature going up or down of the water? It's showing an increase, yes? Okay? So it's going up, right? So let's put our water here because it's gaining energy, correct? Yes? What's giving that water the energy to increase in temperature? It's diluting the acid, yes? So on this side here, we would say sulfuric acid, H2SO4, sulfuric acid. Okay? That's where the energy is coming from. Once again, key in on the words, guys. Calculate the molar enthalpy of the sulfuric acid. Well, gee, I wonder which formula we need to use, right? Probably that one again, yeah? Right? We're looking for delta RH yet again, okay? What's going to go on this side? Well, once again, what do we have? What's gaining energy? The water. Do we know the mass of water? Yes. Do we know C? Yes. Do we know delta T, how much it increases or decreases by? Yes. Okay? So, let's fill this in. How much water do we actually have here? 1,000 milliliters, right? Okay? You took 25 milliliters of the acid, and then you filled it up to 1,000, and that's the important part here. You formed 1,000 milliliters, right? So now you have 1,000 milliliters, and you could calculate the resulting concentration if you wanted to. Okay, so that's going to go here for the mass. 1,000 milliliters is 1,000 grams, which it happens to be 1 kilogram, yes? So a kilogram of water. C, 4.19 joules per gram degree Celsius, and it showed me an increase of 3.25 degrees Celsius, yes? So it doesn't say what the initial or final was, it just says that that's how much it goes up by. What's on the other side? Well, I got negative N here, and of course, once again, the molar enthalpy of the sulfuric acid. What am I gonna, that's what I'm looking for, the kilojoules per mole for this sulfuric acid, right? I thought that was my wife, but it's not. All right. How am I going to find N? Well, once again, how do we find N? Mass over molar mass. Another common one, of course, is C times V. How many moles of sulfuric acid am I starting with? Yes? What's driving this equation? The 25 milliliters of 17.8 molar is what I start with. I add the water, it increases in temperature. Okay? But that's how many moles of sulfuric acid I have. Even after, listen, you might say, why aren't I using the 1,000? Well, remember, even after I add 1,000 milliliters, I still started with this, right? This is what's giving you the increase in the water, the 25 milliliters of 17.8. So 17.8 molar, and of course the 25 milliliters. And that gives me what here? About 0.445 moles. C times V there. Okay? And once again, okay, multiplying the left side, dividing by that number there, 0.445, right? And as you can imagine here, delta RH. So 1 times 4.19 here times our 3.25 divided by 0.445, and I get a negative 30.6 kilojoules per mole. Yes? Okay. Multiply these numbers here, of course. Divide by this number here. Makes sense? Should. Yeah? Sulfuric acid has to be an exothermic molar enthalpy because it is losing energy. That losing energy is going to the water to increase the temperature. Yes? Good? Okay, and that's all you need to do for this one here, by the way. Calculate the molar enthalpy of the diluted solution. So there you go. Okay? Any questions on that? Yes or no? I gave you guys probably 4 examples there. Obviously, the one that we kind of did yesterday, but we kind of finished up today. And then these 3 here. And I'll tell you what, those 4 examples, they're very, very similar to your worksheet today. So you should be kind of able to match them up, obviously. You know, if you need a little bit of help or whatever from somebody, that's fine, ask them, but do so quietly, obviously. But that's kind of what you're looking at for today, okay? And if you understand these, you're probably well on your way. The important thing to remember is you have to look at the system. In most cases, okay, you know, and I don't even know if we do any that do this, water is always going to be part of the system, right? Aqueous solutions or actually just water itself. So, you know, think about that. And remember, by the way, when we do this formula here, is water always going to gain energy? What's an example where water doesn't gain energy? Something that cools down, right? So when we go to lab, we're going to go over these questions tomorrow, so don't freak out. We're going to go over them quite detailed. We'll go over your quiz tomorrow and stuff like that as well. If we have time, we're going to give you probably another quick little question on a quiz or something like that, just for a little review. But tomorrow we're going to go over this, okay? But on Monday we're going to go to lab, and you're going to see that not always does water gain energy. It doesn't always increase in temperature, right? It sometimes goes down. So in this case here, let's say the temperature of water goes down. You know, you start at 10 degrees Celsius and you end up at 0 degrees Celsius. If you did final minus initial there, don't forget, that's a negative 10. It drops, right? Water would have to go on this side in this case, yes? Because it's the one losing the energy. How does it change? Well, probably not a lot, guys. MC delta T probably on this side. Maybe you got to put your delta H over on this side, or maybe you got an MC delta T on this side, right? So maybe you're going to have that times N over on this side here. Okay? Flipped around. Or maybe you got the MC delta T thing here equals that stuff there, MC delta T. Okay? So you have to, you know, always pick the water first, decide which side it's going on, yeah? You know, is it gaining energy or losing energy? And it's pretty obvious to tell. You'll see with the change in the temperature, obviously. Yes? Okay? Any questions? Questions, anyone? So, like I said, make sure you kind of take into consideration what drives the equation, of course. Okay, we have to make sure we know the right number of moles there, what's driving that equation. And secondly, make sure you account for all the water in the system. So if you're mixing 2 solutions together, you need to include both of those volumes. That's how much water is in that system now that you're trying to heat up or cool down in some cases. All right, good? Yeah? All right.